Okay, in this video, we're going to talk about Chapter 6, which deals with multiple random variables. And this is from the book, Introduction to Probability Statistics and Random Variables by PishroNikCh6, an excellent book, which you can find online at www.probabilitycourse.com. All right. Now, what we're going to do is talk about generalizations of topics that we've looked at for simple random variables. Now, let me remind you what we know about the probability mass function and the probability distribution function for real valued random variables. Okay, so if you remember the probability mass function, you use that for a discrete random variable. Discrete means that it can take certain values. So the way that we represented probability mass function was we would represent the possible values of the discrete random variable. And let me call this value 1, value 2, value 3, value 4. Okay? And the way we would represent the probability mass function is we put bars above each value that represent its probability. So the height of this bar, for instance, would represent the probability that your random variable x takes the value v2. Okay? Capital X is used to denote the random variable. Remember, random variable is something like an experiment. We're saying the probability that your experiment results in the value v2 is going to be represented by the height of this bar. All right? So let's think about what a PMF would be in 2 dimensions. So this is discrete and this is also real valued. Okay, so this is a PMF in 2 dimensions. Now here the possible outcomes of our experiment were real numbers, single points. Now, if you have a 2-dimensional random variable, that means your possible outcomes are points in the plane. Okay, so let's say this would be, I call this v1, but now I call it a vector v1. This is a vector v2, vector v3, vector v4. So these would be possible outcomes. Okay, now how would you represent probability mass function? Well, you'd have to use 3 dimensions. You'd have to have a bar with height equal to a probability. So there is a probability that your random variable x is equal to v1. There is a probability that your random variable x is equal to v5 here, and so on. Now, like I said, if you wanted to graph it, you'd need to graph it in 3 dimensions, but just imagine drawing bars in the 3rd dimension above each of these points, with the heights representing the probability. Now, what does it mean for x to be equal to v1? Well, that means that the random variable x, the experiment that you conduct, is a vector of 2 dimensions. It has 2 components. The first component would have to be the first component of v1, and the second component would have to agree with the second component of v1. So I could write this as the probability that x1, which represents the first component of my random variable, which should be the first component of v1, which I'll call x1, little x1, and the second one is the probability that, including the x2 must be, big X2 must be little x2. Let me go through that argument again because I kind of stumbled over my words. If I want the probability, the PMF for this point here, I want the probability that my random variable x is equal to v1. And I probably should put an arrow on over my x just to indicate that x is a vector random variable. I'm sorry, those don't have vector over them because x1 is the first component, x2 is the second component. So if I want the probability that my random variable x is equal to the vector v3, that's going to be equal to the probability that the first component of x, big X that is equal to the first component of V3. I guess I'll call that x prime. And the second component of my random variable is equal to the second component of my vector. Okay. We can relate that exactly to what he has here. Look at what he's done here. It's exactly the same thing, only in multiple dimensions. The probability that this random variable big X, which is represented by n components, the PMF for big X at this n-dimensional point is equal to the probability that each component is equal to the corresponding value. Okay, so that's PMF. Now let's think about PDF, probability density function. Well, recall what we did for PDF for a real valued, regular, one-dimensional random variable. So we'll do PDF for real valued random variable. Now, the way we represent that is we'd have a real line, and then we have our probability density function, which was a usually kind of continuous type function. And remember that the probability of being between A and B was equal to the area underneath this curve. Okay, so I can say the probability that A is between X and B is equal to the integral from A to B of what we called the probability density function of the random variable X, and here we'll put a little x dx. Okay, and recall that the minus infinity to infinity, that integral, the total integral, is going to be equal to 1. Okay, so those were two facts that we used. And of course, the probability density function is positive. All right, so this is the situation for a real valued random variable. Now let's consider for a two-dimensional random variable the probability density function for a two-dimensional random variable. All right, now you're in the plane. All right. So how could we do a probability density function? Well, we have to have a function that's a point of every point of the plane. So you have to imagine a surface. Now, unfortunately, I can't draw very well, but it's a surface over this. Think of a terrain on top of this with mountains and valleys. But this surface, you could think of this as a cross-section of a surface, just showing the side of a mountain, okay? And think of this as the entire terrain of the mountains, okay? So PDF is a surface, and how do we get probabilities from PDF? Well, suppose I want the probability that my random variable X is in this area, okay? So I'm going to find the probability by integration the same way. Okay, so I can call this surface as a function of x and y, or let's just call it x1 and x2. Okay, so this function, I can call it z, well, is equal to some probability density function of two components. Now there's really not much difference here. Instead of just one component, I'm using two. And then I want to, if this is the area A, I want the probability that the random variable X is in A is equal to the integral over A. This is actually going to be a surface integral, so an area integral, so I'll draw two integral signs. It's the area integral of the two-dimensional density dx1 dx2, right? Now, just to make this clear, this x now is a vector random variable with two components. Right, let me relate that back to what he has here. You see, this is the same thing. He's taking a vector random variable. His vector random variable has n components. Okay, he's using the letter F instead of a P, of little p. That's actually more standard. His little f is for the vector big X, which he's writing out in component form. This density takes values on x1, x2 up to xn, and you find the probability of being in area A, or in this case it's going to be a volume or an n volume, by integrating the density over that volume. Okay, so look at this picture, relate it back to the picture I have here. Just remember that in 2 dimensions, the probability density function is a kind of a surface. Now, just to agree with him, I'll go ahead and change this back to a F, because he's calling it F. And he actually writes it out in components, but I'm going to write it as a vector. So big X vector is my shorthand for his x1, x2. So I'm going to have fx here. Okay, so if you keep in mind the 2-dimensional picture, you really can understand the picture in general and dimensions. You just have a function of n variables, and you're doing a volume integral, or in 2 dimension, an area integral, to find the probability.